Before we begin our journey to the edge of a black hole, I have a small request. Many people watch these documentaries, but only a small percentage subscribe. If you enjoy exploring the mysteries of the universe and want to support the channel, please take a moment to subscribe. It is extremely important for the growth of the channel and helps bring more long-form space documentaries to life. Thank you very much. Now, let's begin. Black holes are among the most fascinating and mysterious objects in the universe. They are regions of space where gravity becomes so powerful that nothing, not even light itself, can escape once it passes a certain boundary. Today, black holes are recognized as fundamental components of the cosmos, influencing the evolution of stars, galaxies, and perhaps even the large-scale structure of the universe itself. Yet despite their importance, black holes remained purely theoretical for much of human history. Their story begins not with telescopes or spacecraft, but with gravity. The same force that keeps our feet on Earth and guides planets around the Sun also governs the birth of black holes. To understand how these extraordinary objects form, we must first look at the lives of stars. Every star in the universe exists because gravity continuously pulls matter inward. Deep within a star's core, enormous pressure and temperature allow nuclear fusion to occur. Hydrogen atoms combine to form helium, releasing tremendous amounts of energy. This energy pushes outward, balancing gravity's inward pull. For millions or even billions of years, a star exists in a state of equilibrium between these opposing forces. Gravity tries to collapse the star, while fusion-generated energy prevents that collapse. However, this balance cannot last forever. Stars are not eternal. They are born, they evolve, and eventually they die. The fate of a star depends largely on its mass. Small stars similar to the Sun experience relatively gentle endings. Massive stars, however, live dramatically different lives. They burn their fuel much faster and reach temperatures capable of creating heavier elements. As fusion continues, the star begins producing carbon, oxygen, neon, silicon, and eventually iron. At first, this process helps support the star against gravity. But iron presents a problem. Unlike lighter elements, iron does not release energy when fused. Once a massive star develops an iron core, it approaches the end of its life. The outward pressure generated by fusion begins to weaken while gravity remains relentless. Eventually, the core becomes unstable. In a fraction of a second, the delicate balance that sustained the star for millions of years collapses. Gravity suddenly gains the upper hand. The core contracts at incredible speed, compressing matter to astonishing densities. Temperatures soar into the billions of degrees. Electrons and protons are crushed together, forming neutrons. The collapse becomes so violent that the outer layers of the star rebound outward in one of the most powerful explosions in the universe, a supernova. For a brief period, a single exploding star can outshine an entire galaxy containing hundreds of billions of stars. The explosion scatters heavy elements into space, enriching future generations of stars and planets. The iron in human blood, the calcium in our bones, and many other elements essential for life were forged inside ancient stars that ended their lives in such explosions. Yet while the outer layers are blasted into space, the core remains behind. What happens next depends once again on mass. If the remaining core is relatively small, it may become a neutron star. These extraordinary objects pack more mass than the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons. But if the core is massive enough, even neutron degeneracy pressure cannot stop the collapse. Gravity continues compressing matter inward without limit. The object shrinks further and further. Density rises to unimaginable levels. Eventually, according to Einstein's theory of general relativity, space and time themselves begin to curve so dramatically that a black hole forms. At this moment, a boundary known as the event horizon appears. This invisible surface marks the point beyond which escape becomes impossible. Once matter or light crosses the event horizon, it can never return to the outside universe. To a distant observer, the black hole appears dark because no light escapes from within. Yet the object itself contains enormous mass concentrated within an incredibly small region of space. The birth of a black hole represents one of the most extreme events known to science. It is the ultimate victory of gravity over all opposing forces. Einstein predicted the possibility of such objects through his equations long before they were observed. At first, even Einstein himself found the implications difficult to accept. The idea that gravity could become so strong that it traps light seemed almost impossible. Nevertheless, observations gradually confirmed the existence of black holes. Astronomers detected stars orbiting invisible objects possessing immense mass. They observed powerful X-ray emissions from matter falling toward unseen gravitational monsters. In 2019, humanity achieved a historic milestone when the first image of a black hole's shadow was captured, providing direct visual evidence of one of the universe's strangest creations. Today, scientists know that black holes come in different sizes. Stellar mass black holes form from the deaths of massive stars. Intermediate mass black holes occupy a middle range that remains poorly understood. Supermassive black holes, containing millions or even billions of times the Sun's mass, reside at the centers of most galaxies, including our own Milky Way. Their origins remain one of the greatest mysteries in modern astronomy. Yet regardless of size, every black hole begins with the same fundamental process: gravity overcoming all resistance. As we continue our journey toward the edge of a black hole, we will discover that their formation is only the beginning. The true mysteries emerge after the black hole is born, when space, time, and reality itself begin behaving in ways that challenge human intuition and reveal some of the deepest secrets of the universe. To truly understand a black hole, we must first understand gravity itself. Every object in the universe exerts a gravitational pull on every other object. This force governs the motion of planets, stars, galaxies, and even the largest structures in the cosmos. For centuries, gravity appeared straightforward. Isaac Newton described it as an invisible force acting across space, pulling objects toward one another. His equation successfully explained the motion of planets and many other astronomical phenomena. Yet gravity would eventually reveal itself to be far stranger than Newton imagined. In the early 20th century, Albert Einstein transformed our understanding of the universe through his theory of general relativity. According to Einstein, gravity is not simply a force. Instead, massive objects bend and distort the very fabric of space and time. Planets orbit the Sun not because they are being pulled by an invisible force in the traditional sense, but because they move through curved space-time created by the Sun's mass. This revolutionary idea changed everything. Space and time were no longer passive stages upon which the universe unfolds. They became active participants in cosmic events. Most of the time, these distortions are relatively small. The Earth bends space-time enough to keep us firmly on its surface and guide the Moon in its orbit. The Sun's greater mass produces stronger curvature, shaping the paths of planets throughout the solar system. But Einstein's equations revealed something extraordinary. If enough mass becomes concentrated within a sufficiently small region, the curvature of space-time can become extreme. Under such conditions, gravity does not merely pull objects inward. It reshapes reality itself. This is precisely what happens when a black hole forms. Imagine standing on the surface of Earth and throwing a ball into the sky. If thrown gently, the ball rises briefly before falling back. Throw it faster, and it travels higher before returning. There exists a specific speed known as escape velocity. If an object reaches this speed, it can overcome Earth's gravitational pull entirely and continue into space. For Earth, escape velocity is approximately 11 kilometers per second. Rockets must exceed this speed to leave our planet permanently. Larger and more massive objects possess higher escape velocities. The Sun's escape velocity is about 617 kilometers per second. As mass becomes increasingly concentrated, escape velocity continues rising. Eventually, a remarkable threshold is reached. The escape velocity becomes greater than the speed of light itself. Since nothing can travel faster than light according to modern physics, escape becomes impossible. This defines the boundary of a black hole. Not because gravity pulls light back after it escapes, but because spacetime is curved so dramatically that every possible path leads inward. Light itself cannot find a route out. The region surrounding this boundary is called the event horizon. It represents one of the most important concepts in black hole physics. The event horizon is not a solid surface. It contains no walls, no physical barrier, and no visible marker floating in space. Yet it divides the universe into two fundamentally different regions. Outside the event horizon, escape remains possible. Inside it, every future path leads deeper into the black hole. Once something crosses this invisible boundary, it can never return. This includes particles, planets, stars, spacecraft, and even light itself. To understand how extreme this environment becomes, imagine space as a flowing river. Far from a black hole, the river moves slowly. Objects can easily swim against the current. As one approaches the event horizon, the flow accelerates. At the horizon itself, the river reaches the speed of light. Beyond that point, the current moves faster than light relative to the outside universe. No matter how powerful an engine may be, no traveler can swim against such a flow. Every path leads inevitably inward. This analogy helps illustrate why black holes are often described as traps. Yet they are not cosmic vacuum cleaners sucking everything around them into oblivion. This common misconception appears frequently in popular culture but does not reflect reality. If the Sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting exactly as it does today. The gravitational influence would remain the same because gravity depends on mass, not on whether that mass is a star or a black hole. Objects only become trapped if they venture sufficiently close. Another remarkable consequence of intense gravity involves time itself. According to general relativity, gravity affects the flow of time. Clocks near massive objects run more slowly than clocks farther away. This effect is extremely small on Earth but measurable with modern technology. Satellites used for GPS navigation must account for gravitational time dilation to maintain accuracy. Near a black hole, however, the effect becomes enormous. As an object approaches the event horizon, time slows dramatically relative to distant observers. To someone far away, a spacecraft nearing the horizon appears to move increasingly slowly. Its signals become weaker and more redshifted. Eventually, it seems almost frozen at the edge of the black hole. Yet for the travelers aboard the spacecraft, time continues normally. They do not notice anything unusual at first. This strange difference between perspectives lies at the heart of many black hole paradoxes and remains one of the most fascinating aspects of modern physics. Black holes also reveal a profound connection between gravity and information. When matter falls into a black hole, what happens to the information describing that matter? Does it disappear forever? Can it somehow be preserved? These questions have challenged physicists for decades and continue driving some of the most advanced research in theoretical physics. The struggle to understand black holes has led to major insights into quantum mechanics, thermodynamics, and the nature of spacetime itself. Many scientists believe that solving the mysteries of black holes may ultimately lead to a deeper understanding of the universe than ever before. In many ways, black holes serve as natural laboratories where the laws of physics are pushed to their limits. They allow researchers to study conditions impossible to recreate on Earth. Extreme gravity, distorted time, intense energy, and the boundaries of known science all converge near these objects. As we continue our journey toward the edge of a black hole, we will move beyond its formation and begin exploring the extraordinary environment surrounding it. There, the familiar rules governing our everyday experience begin to break down, and the universe reveals some of its most astonishing secrets. At first glance, a black hole may seem deceptively simple. It appears as a dark region of space from which nothing can escape. No light emerges from it, making direct observation impossible. Yet beneath this apparent simplicity lies one of the most complex and mysterious structures in the universe. Black holes challenge our understanding of physics because they combine gravity, space, time, energy, and information in ways that remain only partially understood. Although black holes cannot be seen directly, scientists have developed detailed models describing their structure. These models reveal that a black hole is not merely an empty hole in space. Instead, it possesses distinct regions, each governed by extraordinary physical laws. To understand our journey toward the edge of a black hole, we must first explore the different components that make up one of nature's most extreme creations. The most familiar feature of a black hole is the event horizon. This invisible boundary marks the point beyond which escape becomes impossible. The event horizon is often imagined as the surface of a black hole, although it is not a physical object. It contains no solid material and offers no resistance to anything crossing it. A spacecraft approaching the horizon would not collide with a wall or experience an impact. Instead, it would simply pass through a region of space where the geometry of spacetime becomes so distorted that all future paths lead inward. For a non-rotating black hole, the radius of the event horizon depends entirely on the object's mass. This boundary is known as the Schwarzschild radius, named after Karl Schwarzschild, the physicist who first found a solution to Einstein's equations describing black holes. If the Earth were somehow compressed into a black hole, its event horizon would measure only about 9 millimeters across. The Sun would need to be compressed into a sphere roughly 6 kilometers in radius to become a black hole. Despite containing enormous mass, black holes themselves can be surprisingly compact. Surrounding the event horizon is a region where gravity becomes increasingly intense. As one approaches this area, space and time behave in unfamiliar ways. Light follows curved paths. Time slows relative to distant observers. Objects experience powerful tidal forces. These effects grow stronger closer to the black hole, creating an environment unlike anything found elsewhere in the universe. For supermassive black holes, the event horizon may span millions of kilometers, while stellar mass black holes possess much smaller horizons. Yet the fundamental physics remains the same regardless of size. Many black holes are surrounded by an accretion disk, one of the brightest phenomena in the universe. Although black holes themselves emit no light, matter falling toward them often becomes incredibly luminous. Gas, dust, and other materials spiral inward rather than plunging directly into the black hole. As this material accelerates, friction and compression heat it to extraordinary temperatures. The resulting disk can glow across multiple wavelengths, producing visible light, ultraviolet radiation, and powerful X-rays. In some cases, the accretion disk outshines entire galaxies. The first image of a black hole released in 2019 did not show the black hole itself. Instead, it revealed the glowing material surrounding the event horizon. The dark central region visible in the image corresponds to the black hole's shadow, created by gravity bending and trapping light. Rotating black holes possess an even more complex structure. In reality, most black holes are expected to rotate because the stars that formed them were already spinning. A rotating black hole is described by the Kerr solution to Einstein's equations. Such objects generate a remarkable phenomenon known as frame dragging. As the black hole spins, it literally drags spacetime around with it. Imagine placing a spinning ball into thick honey. The surrounding fluid begins rotating as well. In a similar way, rotating black holes twist the fabric of spacetime itself. This effect becomes especially important near the black hole, where the distortion grows extreme. The region affected by frame dragging is known as the ergosphere. It lies outside the event horizon and exists only around rotating black holes. Within the ergosphere, spacetime is dragged so strongly that remaining stationary becomes impossible. Everything is forced to move in the direction of the black hole's rotation. Remarkably, theoretical studies suggest that energy can be extracted from this region. A sufficiently advanced civilization might one day exploit the rotational energy of a black hole, tapping into one of the most powerful energy sources in the cosmos. While such ideas remain speculative, they illustrate how strange and fascinating black hole physics can become. At the center of a black hole lies perhaps the greatest mystery of all, the singularity. According to classical general relativity, all the mass of the black hole collapses into a point of infinite density and zero volume. Here, gravity becomes infinitely strong, and the equations of physics break down completely. Space and time as we understand them cease to function. The singularity represents a boundary beyond which current scientific knowledge cannot extend. Most physicists believe that the concept of an infinite density point indicates that general relativity is incomplete. A future theory combining gravity with quantum mechanics may eventually reveal what truly exists at the center of a black hole. Until then, the singularity remains one of the greatest unknowns in science. Another fascinating aspect of black hole structure involves the paths followed by light itself. Around every black hole exists a region known as the photon sphere. At this distance, gravity is strong enough to force light into circular orbits. Photons can literally circle the black hole. However, these orbits are unstable. The slightest disturbance causes light either to escape into space or fall inward toward the event horizon. The photon sphere contributes to many of the visual distortions associated with black holes. Light from distant stars can be bent dramatically, creating warped and sometimes multiple images of the surrounding universe. Modern observations have revealed that black holes are not isolated curiosities. They play essential roles throughout the cosmos. Supermassive black holes reside at the centers of most galaxies, including the Milky Way. Their gravitational influence helps shape galactic evolution. Some launch enormous jets of energetic particles extending thousands of light-years into space. Others regulate star formation through powerful interactions with surrounding gas. Far from being passive objects, black holes actively participate in the life cycles of galaxies. As our journey continues, we move closer to one of the most famous boundaries in all of science, the event horizon itself. This invisible frontier marks the edge of the known and the unknown. Beyond it lies a realm where escape becomes impossible and where the deepest mysteries of space and time await. The closer we approach, the stranger reality becomes, and the more clearly we begin to see why black holes remain among the most captivating objects in the entire universe. Imagine that humanity has finally built a spacecraft capable of traveling safely across interstellar space. After decades of preparation and years of travel, the crew arrives at one of the most extraordinary destinations in the universe, a black hole. From a great distance, the object appears deceptively simple. There is no giant cosmic vacuum cleaner pulling everything inward. There is no glowing tunnel leading into another dimension. Instead, the black hole appears as a dark circular region surrounded by a distorted halo of light. The stars behind it seem twisted and warped. Entire sections of the sky appear bent around an invisible center. Even before reaching the black hole, the crew begins witnessing phenomena unlike anything encountered elsewhere in the cosmos. This is the beginning of the journey toward the event horizon, the point where space, time, and reality itself begin behaving in ways that challenge human intuition. At first, the approach seems uneventful. Far from the black hole, gravity behaves much as it does around any other massive object. The spacecraft can orbit safely without danger. In fact, if the black hole has the same mass as a star, its gravitational influence at large distances is essentially identical. A planet could orbit a black hole just as it orbits a star. The difference emerges only when one moves closer. As the spacecraft gradually descends inward, the visual appearance of the universe begins changing dramatically. Einstein's theory predicts that gravity bends light, and nowhere is this effect more spectacular than near a black hole. Light from distant stars follows curved paths around the object. The sky appears distorted. Some stars seem duplicated because their light reaches the observer along multiple routes. Entire regions of space appear stretched and warped around the dark center. One of the most striking features visible during the approach is the black hole's shadow. Contrary to popular belief, the shadow is not the event horizon itself. Instead, it is a larger dark region created by the black hole's extreme gravity trapping nearby light. Surrounding this shadow is a bright ring produced by photons orbiting the black hole before escaping toward distant observers. This glowing ring was visible in the first historic image of a black hole captured by the Event Horizon Telescope in 2019. To the astronauts approaching the black hole, the sight would be even more extraordinary. The entire universe seems wrapped around the dark sphere. Looking in certain directions, they might literally see the backs of their own spacecraft due to light bending around the black hole. As the journey continues, another strange phenomenon begins to emerge. Time itself starts behaving differently. According to general relativity, gravity slows the passage of time. This effect, known as gravitational time dilation, exists everywhere in the universe but becomes dramatic near a black hole. The closer the spacecraft moves toward the event horizon, the slower its clocks run relative to observers far away. The astronauts themselves notice nothing unusual. Their watches tick normally. Their hearts beat at familiar rates. Conversations proceed naturally. Yet distant observers watching the spacecraft see a very different story unfold. To them, the crew appears to move increasingly slowly as the black hole's gravity affects the flow of time. Suppose a mission control center remains safely far from the black hole. Every radio signal transmitted from the spacecraft takes longer to arrive than expected. The frequencies gradually shift toward lower energies through a process known as gravitational redshift. Messages become slower and weaker. Eventually, mission control sees the spacecraft appearing almost frozen near the event horizon. It never seems to cross the boundary. Instead, it fades gradually from view as its light becomes increasingly redshifted. From the perspective of the distant observers, the spacecraft appears suspended forever at the edge of the black hole. The astronauts experience something entirely different. For them, the journey continues normally. They do not feel time slowing. They do not notice themselves freezing in place. Looking outward, however, they witness a remarkable effect. The external universe appears to accelerate. Events occurring far away seem compressed into shorter periods. Stars evolve more rapidly. Clocks in distant regions run faster. Depending on the size of the black hole and the exact trajectory, the crew could potentially witness enormous spans of future time unfolding beyond the black hole while only hours or days pass aboard their spacecraft. The physical environment also changes as the spacecraft approaches. Gravity becomes increasingly strong, but what matters most is not gravity itself. It is the difference in gravity between different parts of the spacecraft. These differences create tidal forces. On Earth, tidal force is generated by the moon rays' ocean tides. Near a black hole, the same phenomenon becomes vastly more powerful. If the black hole is relatively small, tidal forces may become deadly long before reaching the event horizon. The spacecraft could experience intense stretching forces capable of destroying both machinery and crew. This process becomes even more extreme later in the journey and is often called spaghettification. Supermassive black holes present a surprising exception. Because their event horizons are enormous, tidal forces at the horizon can be relatively gentle. An astronaut approaching a supermassive black hole might cross the event horizon without immediately noticing anything unusual. This counterintuitive fact demonstrates how strange black holes truly are. The most massive examples may actually provide safer conditions for crossing the boundary than their smaller counterparts. As the spacecraft continues inward, communication with the outside universe becomes increasingly difficult. Signals require more energy to escape the growing gravitational well. Radio transmissions become distorted. Visual observations grow more complicated as the surrounding universe appears increasingly warped. The crew realizes that they are approaching a region no human has ever visited. Beyond lies the event horizon, the ultimate point of no return. What makes the event horizon so fascinating is that it is not a physical object. No signpost marks its location. No glowing barrier warns travelers that they have arrived. Yet it represents one of the most important boundaries in the universe. Outside the horizon, escape remains possible. Inside it, every future path leads deeper into the black hole. Crossing this boundary changes the relationship between cause and effect, space and time, and perhaps reality itself. For now, the spacecraft remains just outside the horizon. The crew watches the distorted universe surrounding them while gravity bends light, slows time, and reshapes the fabric of space itself. They are standing at the edge of one of nature's greatest mysteries. Beyond the event horizon lies a realm from which no information can return. It is the frontier separating the known universe from the unknown. And in the next stage of the journey, we will move even closer to that invisible boundary and discover what happens when gravity begins to dominate every aspect of existence. Among all the strange phenomena associated with black holes, perhaps none is more difficult to understand than their effect on time itself. Most people think of time as constant and universal. Seconds pass at the same rate for everyone. Clocks tick steadily. The future arrives one moment after another in an orderly sequence. Yet Einstein's theory of general relativity revealed a startling truth. Time is not absolute. It can stretch, slow down, and flow at different rates depending on gravity and motion. On Earth, these effects are extremely small, but near a black hole they become extraordinary. In fact, a black hole is one of the few places in the universe where the passage of time becomes dramatically different for different observers. As we continue our journey toward the event horizon, we enter a region where time itself begins to lose its familiar meaning. To understand this phenomenon, imagine two identical clocks. One remains far away from a black hole in deep space, while the other is carried aboard our spacecraft as it approaches the event horizon. According to common intuition, both clocks should continue ticking at exactly the same rate. Yet general relativity predicts otherwise. Gravity affects the flow of time. The stronger the gravitational field, the slower time passes relative to regions experiencing weaker gravity. This effect is called gravitational time dilation. It is not science fiction or theoretical speculation. It has been measured countless times using atomic clocks. Even on Earth, clocks located at different altitudes tick at slightly different rates because gravity varies with distance from the planet's center. Modern GPS satellites must account for these differences or navigation systems would quickly become inaccurate. Near a black hole, gravitational time dilation becomes extreme. As the spacecraft moves closer to the event horizon, time aboard the vessel slows relative to distant observers. To the astronauts, everything feels normal. Their biological processes continue unchanged. Conversations proceed naturally. Instruments function as expected. Nothing about their immediate experience suggests that time is behaving differently. Yet for someone watching from far away, the situation appears astonishing. The spacecraft seems to move more slowly. Every action takes longer. Clocks aboard the vessel tick at a reduced rate. The closer the spacecraft gets to the event horizon, the more dramatic this effect becomes. Suppose mission control remains safely distant from the black hole. They observe the spacecraft approaching the horizon through powerful telescopes. Initially, the journey appears normal. But as the vessel nears the boundary, its motion slows. Signals arrive less frequently. The crew's voices become deeper and more stretched due to gravitational redshift. Minutes aboard the spacecraft correspond to increasingly longer periods for distant observers. Eventually, the spacecraft appears almost frozen near the horizon. To mission control, it never actually seems to cross the event horizon. Instead, it gradually fades as its light becomes weaker and redder until it effectively disappears from view. The astronauts witness something entirely different. Looking outward toward the universe beyond the black hole, they see distant clocks running faster. Events unfold more rapidly. Entire stretches of external time become compressed. The closer they move toward the horizon, the more extreme the difference becomes. Depending on the black hole's mass and the spacecraft's trajectory, the crew could potentially observe decades, centuries, or even longer periods passing elsewhere in the universe while experiencing only a relatively short amount of time themselves. In a sense, approaching a black hole allows travel into the future. Not by moving faster than light, but by exploiting differences in the flow of time itself. This idea is not merely theoretical. It arises directly from the mathematics of general relativity and has been confirmed through numerous experiments. Time travel into the future already occurs routinely on tiny scales. Astronauts aboard the International Space Station age slightly differently than people on Earth because of relativistic effects. The differences are extremely small, but they are real. Near a black hole, the effect becomes so powerful that it transforms from a scientific curiosity into a dominant feature of reality. One of the most famous examples illustrating gravitational time dilation appeared in the film Interstellar. In the story, astronauts visit a planet orbiting close to a supermassive black hole. Because of the intense gravity, time passes far more slowly on the planet than elsewhere. A few hours spent on the surface correspond to years passing for people far away. While dramatized for storytelling purposes, the underlying concept is based on real physics. Such extreme differences become possible near sufficiently massive black holes. The relationship between time and gravity reveals something profound about the universe. Space and time are not separate entities. Einstein combined them into a single structure known as space-time. Massive objects curve this structure, influencing both the geometry of space and the flow of time. Near a black hole, the curvature becomes so intense that ordinary intuition breaks down completely. The distinction between space and time begins to blur. Paths through the universe that seem impossible elsewhere become unavoidable. As our spacecraft continues approaching the event horizon, another remarkable consequence emerges. The future becomes increasingly unavoidable. Outside a black hole, people can choose different directions in space. They may travel north, south, east, or west. Time flows forward, but space offers freedom of movement. Inside the event horizon, however, the situation changes dramatically. The singularity lies in the future of every object crossing the boundary. Moving toward the center becomes as inevitable as moving toward tomorrow. This strange connection between gravity and time represents one of the deepest insights provided by general relativity. Physicists continue exploring the implications of these ideas. Time dilation near black holes plays a central role in modern discussions about information, quantum mechanics, and the nature of reality. Some theories suggest that understanding black holes may ultimately lead to a unified description of physics itself. Others propose that black holes contain clues about the origin and fate of the universe. In every case, time remains one of the key pieces of the puzzle. For now, our spacecraft remains just outside the event horizon. The crew watches as the external universe appears to accelerate around them. Stars evolve more quickly. Distant clocks race ahead. The familiar rhythm of time begins to fracture into different experiences depending on perspective. Near a black hole, there is no single universal clock governing reality. Instead, time becomes flexible, shaped by gravity itself. And as we continue moving closer to the horizon, we are about to encounter even stranger effects, where the forces of gravity begin stretching space, matter, and eventually the travelers themselves beyond anything imaginable. As our spacecraft continues its descent toward the event horizon, the universe begins behaving in ways that seem impossible from the perspective of everyday life. On Earth, gravity feels simple. It pulls objects downward, keeps the moon in orbit, and governs the motion of planets around the sun. Yet near a black hole, gravity reveals its true nature. It is no longer merely a force acting on objects. It becomes a powerful distortion of space and time itself. The closer we approach the black hole, the more dramatic these distortions become. Distances no longer behave normally. Light follows unexpected paths. Time slows. The very geometry of reality begins changing. We are entering a realm where Einstein's theory of general relativity dominates every aspect of existence. One of the first effects the crew notices involves vision itself. Looking out the observation windows, the universe appears increasingly distorted. Light from distant stars no longer travels in straight lines. Instead, it follows curved trajectories around the black hole. Entire constellations appear stretched and warped. Stars that should be hidden behind the black hole become visible because their light bends around it. Some objects appear in multiple locations simultaneously. The crew may see several images of the same star occupying different regions of the sky. This phenomenon, known as gravitational lensing, occurs because the black hole's immense gravity acts like a cosmic lens. In some situations, distant galaxies appear as rings, arcs, or strange mirrored patterns surrounding massive objects. Near a black hole, these visual distortions become spectacular. As the spacecraft moves even closer, the crew notices that the universe ahead appears compressed while the universe behind seems stretched. Light from different directions experiences different gravitational effects. Looking outward becomes increasingly confusing because familiar concepts such as straight lines and fixed positions begin losing meaning. The sky itself appears bent around the black hole. The astronauts find themselves surrounded by a view unlike anything a human has ever witnessed. Another remarkable effect involves color. Light climbing away from a black hole loses energy. As it escapes the intense gravitational field, its wavelength stretches. This process is called gravitational redshift. Blue light gradually shifts toward red. Higher energy radiation becomes lower energy radiation. To distant observers watching the spacecraft, signals transmitted from near the black hole become increasingly redder and weaker. Eventually, they fade almost completely. Conversely, the crew approaching the black hole may observe incoming light from certain directions becoming blue-shifted. Light gains energy as it falls deeper into the gravitational field. Colors become distorted. The appearance of the universe changes in ways impossible to experience elsewhere. Extreme gravity also affects the physical dimensions of space itself. Distances near a black hole behave differently than ordinary intuition suggests. To distant observers, the spacecraft seems to require an infinite amount of time to reach the event horizon. Yet for the crew, the journey continues normally. This discrepancy emerges because gravity changes not only the flow of time but also the structure of space. Measurements that appear straightforward far from the black hole become deeply complicated near it. The closer one approaches the event horizon, the more space and time intertwine into a geometry unlike anything encountered in everyday experience. The crew soon begins observing another extraordinary phenomenon. The stars behind the black hole appear brighter than expected. This occurs because the black hole concentrates light through gravitational lensing. In some directions, entire regions of the sky appear magnified. Objects normally too distant to observe become temporarily visible. Interestingly, the severity of tidal forces depends strongly on the size of the black hole. Smaller stellar mass black holes generate intense tidal effects near the event horizon. A human approaching such an object would likely be destroyed before reaching the boundary. Supermassive black holes behave differently. Because their event horizons are enormous, tidal forces at the horizon can be surprisingly gentle. An astronaut crossing the event horizon of a supermassive black hole might initially survive without noticing anything unusual. This counterintuitive fact remains one of the strangest aspects of black hole physics. The largest black holes may provide the smoothest passage across the point of no return. Meanwhile, time dilation continues growing more pronounced. The crew watches the outside universe accelerating around them. Distant stars evolve faster. External clocks race ahead. Entire civilizations could potentially rise and fall while only a short period passes aboard the spacecraft. The realization is both fascinating and unsettling. The astronauts are effectively becoming travelers into the future. Every minute spent near the black hole corresponds to larger intervals passing elsewhere in the cosmos. The combination of gravitational lensing, time dilation, redshift, and tidal forces creates an environment unlike any other known location in the universe. Here, gravity influences not only matter but information, light, and the very structure of reality. Concepts that seem obvious on Earth begin breaking down. Up and down lose meaning. Straight lines become curved. Time becomes relative. Space becomes distorted. The black hole reveals that reality is far stranger than human intuition ever suggested. For physicists, these effects are not merely curiosities. They provide crucial insights into the nature of the universe. Black holes serve as testing grounds where general relativity operates under its most extreme conditions. Every strange phenomenon observed near them confirms and extends our understanding of Einstein's theories. Yet black holes also expose the limits of current physics. The deeper we investigate them, the more questions emerge. Gravity explains much of what we see, but mysteries remain waiting beyond the event horizon. Our spacecraft now hovers dangerously close to that invisible boundary. The crew has witnessed light bending, time slowing, and space warping around them. Yet even stranger experiences await. Ahead lies a phenomenon so extreme that it has become one of the most famous consequences of black hole physics. It is a process capable of stretching matter itself into long, thin strands through overwhelming gravitational forces. Scientists have given this terrifying effect a surprisingly humorous name, spaghettification. And as our journey continues, we are about to discover exactly what happens when gravity begins pulling different parts of an object with dramatically different strength. Among all the strange and often terrifying consequences of black hole physics, few are as famous as spaghettification. The name may sound humorous, almost cartoonish, but the phenomenon itself is very real. It describes what happens when an object enters a region where gravitational forces vary dramatically across its length. Near a black hole, gravity does not pull equally on every part of an object. The side closest to the black hole experiences a stronger pull than the side farther away. This difference creates powerful tidal forces capable of stretching and compressing matter in extraordinary ways. If those forces become extreme enough, they can literally tear apart stars, planets, spacecraft, and even human bodies. As our journey continues toward the event horizon, we are about to encounter one of the most dramatic demonstrations of gravity's power. To understand spaghettification, imagine standing on Earth. Gravity pulls equally on your head and your feet. There is a tiny difference because your feet are slightly closer to Earth's center, but the effect is so small that it is completely unnoticeable. Now imagine a much stronger gravitational field. The closer you move toward the source of gravity, the larger these differences become. Near a black hole, the disparity can become enormous. If your feet are slightly closer to the black hole than your head, gravity pulls harder on your feet. At the same time, the sides of your body experience forces directed inward. The result is a stretching effect along one direction and a squeezing effect along another. Physicists call these tidal forces because they arise from the same basic mechanism that produces tides on Earth, though on a vastly greater scale. The process begins gradually. As the spacecraft approaches the black hole, instruments record increasing stress along the vessel's structure. The difference in gravitational pull between the front and rear sections becomes measurable. Engineers designed the craft to withstand enormous forces, but eventually even advanced technology faces limits. If the black hole is relatively small, tidal forces near the event horizon become extraordinarily intense. Metal structures begin stretching. Mechanical systems experience strain. The crew notices objects drifting slightly out of alignment as gravity acts unevenly across the spacecraft. For a human being, the consequences would be devastating. Imagine falling feet first toward a stellar mass black hole. Gravity pulls more strongly on your feet than your head. The difference increases rapidly as you descend. Your body begins stretching along the direction of motion. Simultaneously, tidal forces compress you sideways. The effect resembles pulling a piece of dough into a long, thin strand. Eventually, tissues, organs, bones, and even molecules can no longer withstand the stress. The body is torn apart and stretched into an ever thinner stream of matter. This is the origin of the term spaghettification. Matter becomes elongated into shapes resembling strands of spaghetti. One of the most remarkable aspects of this process is that it depends heavily on the size of the black hole. Smaller black holes generate stronger tidal forces near the event horizon because their mass is concentrated within a smaller region. A stellar mass black hole may spaghettify an astronaut long before the event horizon is reached. The journey ends before the traveler ever crosses the point of no return. Supermassive black holes behave differently. Their event horizons are vastly larger. Although they contain far more mass, the gravitational gradient at the horizon can actually be gentler. An astronaut approaching a supermassive black hole might cross the event horizon without immediately experiencing dangerous tidal forces. In this strange way, the largest black holes can be less deadly at the horizon than smaller ones. This surprising fact creates one of the most fascinating scenarios in black hole physics. Imagine falling into the supermassive black hole at the center of a galaxy. As you cross the event horizon, nothing dramatic happens at that exact moment. There is no shockwave, no flash of light, and no physical barrier. Your clocks continue ticking normally. Your spacecraft remains intact. Looking around, you might not even know that the horizon has been crossed. Yet despite this seemingly calm transition, your fate has already been sealed. Escape has become impossible. Every possible future path now leads deeper into the black hole. Spaghettification eventually becomes unavoidable even inside a supermassive black hole. As you move closer to the center, tidal forces continue increasing. The stretching grows stronger. The compression intensifies. Regardless of size, every black hole contains regions where gravity becomes overwhelmingly destructive. The difference lies only in how long the process takes and how close it occurs relative to the event horizon. Astronomers have observed evidence of spaghettification occurring on cosmic scales. Occasionally, a star wanders too close to a supermassive black hole at the center of a galaxy. The star experiences intense tidal forces that tear it apart. Streams of stellar material spiral around the black hole, forming brilliant accretion disks visible across enormous distances. These events are known as tidal disruption events and rank among the most energetic phenomena in the universe. For a brief period, the destruction of a single star can produce extraordinary amounts of radiation, allowing astronomers to study black holes that might otherwise remain hidden. The physics behind spaghettification reveals something profound about gravity. Most people think of gravity as a force that pulls objects together. Yet gravity can also tear objects apart. The same mechanism responsible for holding galaxies together can destroy matter when concentrated intensely enough. Black holes represent the ultimate expression of this dual nature. They gather matter through gravity while simultaneously generating forces capable of overwhelming the structures they attract. The crew aboard our spacecraft understands these realities all too well. Their instruments show tidal forces increasing steadily. The black hole's influence grows stronger with every kilometer traveled. They have crossed into a realm where gravity dominates absolutely. The familiar laws governing everyday experience no longer provide reliable intuition. Survival depends entirely on the properties of the black hole itself. Yet spaghettification, terrifying as it may be, is only part of the story. Ahead lies the most famous boundary in all of black hole physics, the event horizon. This invisible frontier marks the point where escape becomes impossible and where space and time exchange roles in ways that challenge even the most advanced scientific understanding. What happens when a traveler finally reaches that boundary? Does anything special occur at the exact moment of crossing? Can anyone know that the point of no return has been passed? As our journey continues, we are about to confront one of the deepest mysteries in the universe and take our first step beyond the edge of known reality. After a journey through warped space, distorted light, extreme gravity, and the terrifying prospect of spaghettification, our spacecraft has finally arrived at the most famous boundary in the universe, the event horizon. This invisible frontier separates the known from the unknown. Outside it, information can still escape. Light can travel outward. Spacecraft can turn around and return home. Inside it, every possible future leads deeper into the black hole. For decades, scientists, writers, and filmmakers have imagined what it would be like to cross this boundary. Would there be a violent shockwave? A sudden flash of light? A wall of energy? Surprisingly, according to Einstein's theory of general relativity, the answer may be no. Under the right conditions, crossing the event horizon could be one of the most uneventful moments of the entire journey. To understand why, it is important to remember that the event horizon is not a physical surface. It is not made of matter. It has no texture, color, temperature, or solid structure. It is a mathematical boundary within space-time itself. The event horizon marks the location where escape velocity becomes equal to the speed of light. Outside this boundary, light can still move away from the black hole. At the horizon, escape becomes impossible. Yet nothing physical announces its presence. An astronaut approaching the event horizon of a sufficiently large black hole might see nothing unusual at the exact moment of crossing. From the crew's perspective, everything seems normal. Their clocks continue ticking. The spacecraft remains intact. Instruments operate correctly. Looking around the cabin, nothing appears different. The event horizon leaves no obvious mark on the traveler. There is no cosmic alarm signaling that the point of no return has been reached. If the black hole is supermassive and tidal forces remain weak, the crew may cross the horizon without realizing it. Only later, after analyzing their data, might they discover that the boundary has already been passed. Yet while the local experience appears ordinary, something profound has happened. The structure of space-time itself has changed. Outside the event horizon, the crew could choose different futures. They might travel toward the black hole, away from it, or orbit around it. Inside the event horizon, those choices disappear. Every possible path through space-time leads inward. Moving toward the singularity becomes as inevitable as moving toward tomorrow. This is one of the strangest consequences of general relativity. Inside a black hole, the singularity lies in the future. Just as no one can avoid moving forward through time, nothing inside the event horizon can avoid moving toward the center. To distant observers, however, a completely different story unfolds. Mission Control watching from afar never sees the spacecraft cross the horizon. Instead, the vessel appears to slow down more and more as it approaches the boundary. Its clock seems to tick increasingly slowly. Signals become redder and weaker. Eventually, the spacecraft fades from view. To outside observers, it appears frozen at the edge forever. This creates one of the most famous paradoxes in black hole physics. The astronauts experience themselves crossing the horizon, while distant observers never witness the crossing at all. Both descriptions are correct within their respective frames of reference. This strange disagreement arises because time itself behaves differently for different observers. Near the event horizon, gravitational time dilation becomes extreme. The crew experiences only a short period of time while the outside universe continues evolving normally. From their perspective, they pass through the horizon and continue inward. From the outside perspective, they seem trapped at the boundary indefinitely. The universe offers no single universal viewpoint capable of resolving this difference. Reality depends upon where the observer is located. Once inside the event horizon, communication with the outside universe becomes impossible. Any radio signal transmitted outward remains trapped by the black hole's gravity. Light emitted by the spacecraft can no longer escape. Information itself becomes imprisoned. This fact has enormous implications for physics because it raises a troubling question. What happens to information that enters a black hole? Does it disappear forever? Is it somehow stored on the event horizon? Can it eventually escape? These questions form the foundation of the famous black hole information paradox, one of the greatest unsolved problems in modern science. As the spacecraft continues deeper, the visual appearance of the universe becomes increasingly bizarre. Light from outside still enters the black hole and reaches the crew. They can continue observing the external universe for some time after crossing the horizon. However, the view becomes increasingly distorted. The black hole's gravity bends incoming light into unusual patterns. The sky appears compressed into strange shapes. Familiar constellations disappear. The geometry of space itself becomes increasingly alien. Inside the event horizon, another unsettling realization emerges. There is no way back. Outside the horizon, turning around was always an option. Powerful engines could potentially overcome gravity and carry the spacecraft away. Now, no engine ever built or imagined can help. The issue is not insufficient power. The problem is that escape would require moving faster than light, something forbidden by known physics. The crew has entered a region from which every future path leads deeper inward. This inevitability makes the event horizon fundamentally different from any boundary encountered elsewhere in the universe. Crossing the horizon does not immediately destroy the spacecraft. It does not necessarily harm the crew. Yet it changes their destiny completely. Every second that passes carries them closer to the singularity. The center of the black hole has become their future, just as tomorrow is the future for people living on Earth. Scientists continue debating whether this classical picture remains entirely correct. Some modern theories suggest that quantum effects may alter the nature of the event horizon. Concepts such as firewalls, holographic information storage, and quantum gravity propose modifications to the traditional description. These ideas remain controversial and unconfirmed. For now, Einstein's general relativity provides the best available guide, and according to that theory, crossing the event horizon is surprisingly uneventful from the traveler's perspective. Yet the calm cannot last forever. The deeper the spacecraft moves into the black hole, the stronger gravity becomes. Tidal forces continue increasing. Space-time grows increasingly distorted. The singularity draws nearer. Beyond the event horizon lies a realm where no observation has ever been made and where current physics begins approaching its limits. Ahead waits the greatest mystery of all: what truly exists inside a black hole? Is there really a singularity? Does space and time come to an end? Or does reality hide something even stranger beyond the horizon? As our journey continues, we move toward the deepest unknown in the universe. Once the event horizon has been crossed, the rules that govern the familiar universe begin to unravel. Outside the black hole, astronomers can observe stars, galaxies, planets, and the flow of time. Inside, however, no information can escape. This simple fact creates one of the greatest mysteries in science. What actually exists beyond the event horizon? The truth is both fascinating and frustrating. No human has ever observed the interior of a black hole, and according to known physics, no information from inside can return to tell the story. Everything scientists know about black hole interiors comes from mathematics, theoretical models, and the laws of physics themselves. Yet these laws sometimes produce answers so strange that even the greatest physicists struggle to fully understand them. According to Einstein's theory of general relativity, once an object crosses the event horizon, its journey toward the center becomes unavoidable. Unlike ordinary movement through space, where multiple directions remain available, every future path inside a black hole points inward. The singularity lies ahead just as tomorrow lies ahead in time. This is one of the most bizarre predictions ever produced by science. Space and time exchange roles in a sense. Outside the black hole, moving toward the center is a choice. Inside, it becomes a certainty. The closer one approaches the center, the more extreme the environment becomes. Gravity grows stronger. Tidal forces increase dramatically. Space-time becomes increasingly curved. The equations of general relativity predict that all matter eventually reaches a location known as the singularity. Here, density becomes infinite. Volume becomes zero. Curvature becomes infinite. The laws of physics break down completely. Mathematics itself begins producing nonsensical results. Infinite values appear everywhere. For physicists, this is a warning sign. Nature rarely allows infinities to exist physically. Instead, infinities usually indicate that a theory has reached the limits of its applicability. This realization has led many scientists to suspect that singularities do not truly exist as described by classical general relativity. Instead, something else may happen at extremely small scales where quantum effects become important. Unfortunately, modern physics currently lacks a complete theory capable of combining general relativity with quantum mechanics. Gravity governs large-scale structures such as stars and galaxies. Quantum mechanics governs the microscopic world of particles and atoms. Both theories work extraordinarily well within their respective domains. Yet inside a black hole, both become essential simultaneously. This makes black holes one of the most important testing grounds for the future of physics. One possibility is that quantum gravity prevents the formation of an actual singularity. Instead of collapsing into an infinitely dense point, matter may reach a state where quantum effects resist further compression. Various theoretical models propose alternatives. Some suggest that black holes contain extremely dense cores rather than singularities. Others predict entirely new states of matter unlike anything currently known. Until a complete theory of quantum gravity is developed, these possibilities remain speculative. Among the most intriguing ideas is the possibility that black holes may connect to other regions of space-time. Certain solutions to Einstein's equations permit structures known as wormholes. These hypothetical tunnels could connect distant locations within the universe or perhaps even entirely separate universes. In popular science fiction, black holes are often portrayed as gateways through such tunnels. However, current evidence provides no confirmation that real black holes function this way. Most theoretical wormholes appear unstable and would likely collapse before anything could pass through them. Nevertheless, the mathematics remain sufficiently intriguing that physicists continue exploring the possibility. Another remarkable idea emerges from quantum mechanics itself. Some researchers propose that information entering a black hole is not destroyed but somehow preserved. This question became especially important after physicist Stephen Hawking made one of the most revolutionary discoveries in modern theoretical physics. In the 1970s, Hawking demonstrated that black holes are not completely black. Quantum effects near the event horizon allow them to emit tiny amounts of radiation, now known as Hawking radiation. Over enormous periods of time, this radiation causes black holes to lose mass and eventually evaporate. The existence of Hawking radiation creates a profound puzzle. If a black hole eventually disappears, what happens to all the information contained within the matter that fell into it? Quantum mechanics insists that information cannot simply vanish. Yet Hawking's original calculations suggested that information might be lost forever. This conflict became known as the black hole information paradox. Decades later, it remains one of the greatest unsolved problems in theoretical physics. Some modern theories suggest that information is encoded on the event horizon itself. Others propose that information escapes through subtle correlations within Hawking radiation. One particularly influential idea is the holographic principle. According to this concept, all the information contained within a three-dimensional volume may be encoded on a two-dimensional surface surrounding it. If true, a black hole could function like a cosmic hologram, storing information on its boundary rather than within its interior. This extraordinary idea has influenced many areas of modern theoretical physics and may eventually help explain the nature of reality itself. Meanwhile, our spacecraft continues falling inward. The crew understands that they are entering a region humanity can describe mathematically but cannot observe directly. Every instrument aboard the vessel records increasingly extreme conditions. The black hole's gravity dominates every aspect of their environment. Communication with the outside universe has long since become impossible. No message can escape. No rescue can arrive. The astronauts are moving toward a destination hidden behind one of nature's most absolute barriers. Looking outward, they can still observe distorted light entering from the external universe. Looking inward, however, they face the greatest unknown in modern science. Does a singularity truly await them? Will quantum gravity reveal an entirely different reality? Could space and time themselves transform into something fundamentally new? No one knows. This uncertainty is precisely what makes black holes so important. They are not merely exotic astronomical objects. They represent the point where humanity's current understanding of nature begins to fail. Every mystery surrounding black holes points toward deeper truths waiting to be discovered. Somewhere beyond the event horizon, hidden behind the most extreme gravity in the universe, may lie clues capable of transforming physics forever. As our journey continues, we move even closer to the mysterious center of the black hole. There, according to classical theory, waits the singularity itself, the ultimate destination of every object that crosses the horizon and perhaps the most enigmatic location in the entire cosmos. At the heart of every black hole, according to Einstein's theory of general relativity, lies one of the most mysterious concepts in all of science, the singularity. It is a place where the known laws of physics appear to break down completely. Density becomes infinite. Space-time curvature becomes infinite. Volume shrinks to zero. These words are difficult to imagine because infinity does not exist anywhere else in nature as far as we know. Whenever physicists encounter infinities in their equations, it usually signals that something is missing from the theory. Yet black holes force scientists to confront precisely such a situation. Deep within these cosmic monsters, hidden beyond the event horizon, the mathematics points toward a region where our understanding of reality reaches its limit. To appreciate the significance of the singularity, imagine compressing matter more and more. A cloud of gas collapses into a star. A star exhausts its fuel and collapses into a white dwarf or neutron star. Gravity continues squeezing matter into increasingly smaller volumes. In a neutron star, atoms themselves are crushed. Electrons and protons merge into neutrons, creating one of the densest forms of matter known. Yet even neutron stars possess limits. If enough mass is present, gravity overwhelms every known force resisting collapse. Matter continues falling inward. According to classical general relativity, nothing can stop the process. Compression proceeds endlessly until all mass becomes concentrated into a single point. This hypothetical endpoint is the singularity. The concept sounds simple, but its implications are staggering. Infinite density means that all the mass of a star, or perhaps millions or billions of stars in the case of supermassive black holes, is compressed into an infinitely small location. Such conditions cannot be recreated in laboratories. No telescope can observe them directly. The singularity remains hidden behind the event horizon, forever shielded from the outside universe. Yet despite its invisibility, it plays a central role in black hole physics. One reason physicists are skeptical of singularities is that infinities generally indicate incomplete understanding. For example, before the development of quantum mechanics, classical theories predicted certain infinities that later disappeared once a deeper framework was discovered. Many researchers suspect the same thing is happening here. The singularity may not be a real physical object but rather a sign that general relativity is incomplete under extreme conditions. Somewhere near the center of a black hole, a more fundamental theory may replace Einstein's description and reveal what truly happens. The leading candidate for such a theory is quantum gravity. Modern physics rests upon two extraordinarily successful frameworks. General relativity explains gravity and large-scale structures. Quantum mechanics explains particles and microscopic phenomena. Each theory works remarkably well in its own domain. The problem arises when both become important simultaneously. Near the singularity, gravity is immensely strong while distances become unimaginably small. This is precisely the regime where both theories should operate together. Unfortunately, physicists do not yet possess a complete theory combining them. As a result, the true nature of the singularity remains hidden. Several theoretical approaches attempt to solve this mystery. One possibility comes from loop quantum gravity, which suggests that space itself may have a fundamental discrete structure. Instead of being infinitely divisible, space could consist of tiny building blocks. If this idea is correct, collapse might eventually hold because space cannot be compressed beyond a certain limit. The singularity would be replaced by an extremely dense quantum state rather than an infinite point. String theory offers another possibility. According to this framework, the fundamental constituents of reality are not point-like particles but tiny vibrating strings. Under extreme conditions, the behavior of these strings may prevent true singularities from forming. Some versions of string theory even suggest that black holes contain complicated internal structures far richer than classical physics predicts. While these ideas remain speculative, they illustrate how modern theoretical physics is attempting to move beyond the concept of infinite density. Another fascinating proposal involves the idea of a black hole bounce. In certain models, collapsing matter never reaches infinite density. Instead, quantum effects generate enormous pressure that eventually reverses the collapse. Rather than ending in a singularity, the matter rebounds. Some researchers have even suggested that such processes could create entirely new universes. In this view, every black hole might serve as the birthpoint of another cosmos. The universe we inhabit could itself have originated from the interior of a black hole existing within a larger parent universe. Although highly speculative, these ideas demonstrate how black holes continue inspiring some of the boldest concepts in modern science. The singularity also plays a role in one of the most profound philosophical questions ever asked. Do the laws of physics remain valid everywhere? Most scientific theories assume that nature follows consistent rules. Yet the singularity appears to represent a place where those rules cease functioning. If such regions truly exist, they may mark the boundaries of scientific explanation itself. Understanding what happens there is not merely an astronomical problem. It is a question about the nature of reality. Meanwhile, our spacecraft continues its inevitable descent. According to classical theory, every second brings the crew closer to the singularity. Tidal forces continue growing stronger. Space-time becomes increasingly distorted. The astronauts know that they are approaching a region no observation can confirm and no experiment can directly test. Everything humanity knows about this place comes from equations written far away from the black hole itself. Looking outward, the external universe appears increasingly compressed and distorted. Looking inward, the path leads toward one of the greatest mysteries in science. Does an infinitely dense singularity truly await? Will quantum gravity reveal an entirely different structure? Could black holes contain bridges to other regions of space-time or even other universes? No definitive answers exist. What makes the singularity so important is that it sits at the intersection of everything physicists hope to understand. Gravity, quantum mechanics, information, space, time, and the origin of the universe all converge here. Solving the mystery of the singularity may ultimately reveal a deeper theory capable of explaining reality more completely than ever before. And yet, despite decades of research, the singularity remains hidden behind the event horizon, inaccessible to direct observation. It is the ultimate unknown. But black holes influence far more than the fate of objects falling into them. Some have grown to truly unimaginable sizes, containing millions or even billions of times the mass of the Sun. These giants sit at the centers of galaxies and shape the evolution of entire cosmic structures. To understand the full significance of black holes, we must now turn our attention to the largest examples in the universe, the supermassive black holes that rule the hearts of galaxies. When most people think of black holes, they imagine the remnants of massive stars that collapsed under their own gravity. These stellar mass black holes are indeed extraordinary, typically containing several times the mass of the Sun. Yet they are dwarfed by another class of objects so enormous that they challenge the limits of imagination. These are supermassive black holes, the giants that occupy the centers of galaxies. While a stellar black hole may contain 10 or 20 solar masses, a supermassive black hole can contain millions or even billions of times the mass of the Sun. They are among the largest and most influential structures in the known universe, shaping the evolution of entire galaxies and perhaps playing a critical role in the history of cosmic structure itself. The existence of supermassive black holes was once considered highly speculative. Astronomers knew that many galaxies displayed unusual activity at their centers. Some emitted enormous quantities of radiation. Others launched colossal jets of particles extending thousands of light-years into space. These energetic phenomena seemed far too powerful to be explained by ordinary stars. As observations improved, evidence gradually accumulated suggesting that something extraordinarily massive lurked in galactic cores. Eventually, the conclusion became unavoidable. Hidden within the centers of most galaxies were gigantic black holes whose masses far exceeded anything produced by ordinary stellar collapse. Our own Milky Way contains one of these giants. At the center of the galaxy lies a supermassive black hole known as Sagittarius A star. For decades, astronomers could not see it directly because dense clouds of gas and dust obscured the galactic core. Instead, they studied the motions of nearby stars. These stars moved around an invisible object with incredible speeds. By carefully tracking their orbits, scientists calculated the mass of the hidden object. The results were astonishing. More than 4 million solar masses occupied a region smaller than our solar system. No known object other than a black hole could explain such observations. The confirmation of Sagittarius A* represented a major breakthrough, but it soon became clear that the Milky Way's black hole is relatively modest compared to others in the universe. Some galaxies contain monsters with masses reaching billions of suns. One famous example resides in the giant elliptical galaxy M87. This black hole contains roughly 6.5 billion solar masses and became historically significant in 2019 when the Event Horizon Telescope captured the first image of a black hole shadow. The image showed a glowing ring of hot material surrounding a dark central region, providing direct visual evidence of a black hole's existence. For the first time, humanity had effectively photographed one of the most extreme objects in nature. The size of these giants is difficult to comprehend. The event horizon of Sagittarius A* would comfortably fit inside the orbit of Mercury. The event horizon of the black hole in M87 is far larger, extending across a region comparable to the size of our solar system. If placed where the Sun currently resides, such an object would engulf the orbits of multiple planets. Yet despite their enormous size, supermassive black holes remain surprisingly sparse. Their immense masses are distributed across huge volumes, meaning their average density can actually be lower than that of water. This counterintuitive fact highlights how differently black holes behave from ordinary objects. One of the greatest mysteries surrounding supermassive black holes concerns their origin. Stellar black holes form when massive stars collapse, but this process alone struggles to explain the existence of billion solar mass giants observed in the early universe. Some quasars, powered by supermassive black holes, already existed less than 1 billion years after the Big Bang. There simply may not have been enough time for ordinary stellar black holes to grow into such enormous objects. Astronomers continue debating how these giants formed so quickly. Perhaps they originated from the direct collapse of massive gas clouds. Perhaps they grew through mergers of smaller black holes. Or perhaps entirely new mechanisms operated in the young universe. The answer remains unknown. What is clear is that supermassive black holes profoundly influence their host galaxies. For many years, scientists assumed galaxies formed first and black holes appeared later. Modern observations suggest a far more complex relationship. The mass of a galaxy's central black hole is closely correlated with properties of the galaxy itself. Larger galaxies tend to host larger black holes. This connection implies that black holes and galaxies evolve together. Somehow, the growth of one influences the growth of the other. The mechanism responsible for this relationship appears to involve enormous amounts of energy. As matter falls toward a supermassive black hole, it forms an accretion disk. Friction and compression heat the material to extraordinary temperatures, causing it to emit intense radiation. In some cases, magnetic fields channel part of this energy into powerful jets that shoot outward at nearly the speed of light. These jets can extend thousands or even millions of light-years into intergalactic space. The energy released by a feeding black hole can regulate star formation across an entire galaxy. Too much gas falling inward may trigger powerful outflows that push material away, preventing new stars from forming. In this way, black holes act as cosmic regulators, helping determine how galaxies evolve over billions of years. Some active galactic nuclei are so luminous that they outshine all the stars in their galaxies combined. These objects, known as quasars, rank among the brightest phenomena in the universe. Their power comes not from nuclear fusion, like ordinary stars, but from matter falling into supermassive black holes. The process converts gravitational energy into radiation with remarkable efficiency. A quasar can release more energy in a short period than entire galaxies containing hundreds of billions of stars. For the crew of our spacecraft, descending toward the center of a supermassive black hole offers a unique advantage. The enormous size of the event horizon means tidal forces near the boundary are relatively weak. Unlike a stellar mass black hole, where spaghettification might occur before the horizon is reached, a supermassive black hole allows travelers to venture deeper before encountering destructive forces. This makes such objects ideal settings for our thought experiment. If any black hole could potentially permit an astronaut to cross the horizon intact, it would be one of these giants. Yet even supermassive black holes cannot protect travelers forever. The deeper one ventures, the stronger gravity becomes. The singularity still lies ahead. Space-time continues warping in increasingly extreme ways. And beyond the scientific question surrounding black holes lies another possibility that has fascinated physicists and science fiction writers alike for decades. Could black holes be more than cosmic dead ends? Could they connect to other regions of space, other universes, or entirely new realities? As we continue our journey, we will explore one of the most speculative yet captivating ideas in modern theoretical physics, the possibility that black holes may serve as gateways to something beyond our universe. Few ideas in modern physics capture the imagination quite like the possibility that black holes may be gateways to somewhere else. For decades, scientists, philosophers, and science fiction writers have wondered whether these mysterious objects are more than cosmic traps. Could they connect distant regions of space? Could they lead to entirely different universes? Could falling into a black hole transport a traveler somewhere beyond the observable cosmos? These questions remain speculative, and no evidence currently proves such possibilities. Yet the mathematics of general relativity has produced some astonishing solutions that continue to intrigue physicists. As our journey carries us deeper into the black hole, we arrive at one of the most fascinating and controversial ideas ever proposed. The origin of this concept can be traced back to Einstein's equations. Shortly after general relativity was developed, physicists discovered that the equations permitted unusual structures known as Einstein-Rosen bridges. These bridges, later called wormholes, appeared to connect separate regions of space-time. In principle, a wormhole could act as a shortcut through the universe. Instead of traveling across vast distances through ordinary space, a spacecraft might enter one end of the tunnel and emerge somewhere else entirely. The mathematics seem to allow such possibilities, at least under certain conditions. At first glance, black holes appeared closely related to these hypothetical tunnels. Some solutions suggested that a black hole might possess a corresponding white hole on the other side. A white hole is essentially the reverse of a black hole. While black holes allow matter to enter but not escape, white holes would allow matter to escape but prevent anything from entering. According to certain theoretical models, a black hole and a white hole could be connected through a wormhole. Matter entering one side might emerge from the other. The idea is undeniably captivating. Imagine crossing the event horizon and discovering that the black hole is not an ending but a passage. Instead of being crushed by gravity, travelers might emerge elsewhere in the cosmos. Entire galaxies could be connected through hidden tunnels woven into the fabric of space-time. Distances that normally require millions of years to cross might be traversed almost instantly. Such possibilities have inspired countless stories, but reality appears more complicated. The main problem involves stability. Theoretical wormholes predicted by classical general relativity tend to collapse extremely quickly. The tunnel pinches shut before anything can pass through it. To keep a wormhole open, physicists believe some form of exotic matter would be required. This hypothetical material would possess negative energy density, a property unlike anything encountered in ordinary matter. While certain quantum effects can produce tiny amounts of negative energy under special circumstances, no known process can generate the enormous quantities needed to stabilize a traversable wormhole. Even if stable wormholes exist, another challenge remains. The interior of a realistic black hole is an extraordinarily hostile environment. Extreme gravity, intense radiation, and tidal forces make survival difficult. Many theoretical studies suggest that travelers attempting to use a black hole as a gateway would encounter destructive conditions long before reaching any hypothetical exit. The mathematics permits intriguing possibilities, but nature may impose practical barriers. Yet black holes continue generating new ideas. Some modern theories propose that black holes may create entirely new universes rather than connecting existing ones. According to these models, matter collapsing into a black hole might trigger the birth of a new expanding region of space-time. From the perspective of observers inside that region, it would resemble a Big Bang. Their universe would expand and evolve independently, completely disconnected from the parent universe except through the black hole that created it. This concept leads to a remarkable possibility. If black holes create new universes, then our own universe might have originated inside a black hole existing within another cosmos. In this scenario, every black hole becomes a potential seed for a new universe. Cosmic evolution would operate on scales far beyond anything previously imagined. Universes would give birth to other universes through black holes, creating an immense cosmic family tree stretching across realities beyond direct observation. Although highly speculative, these ideas attract attention because they address several important questions. They offer potential explanations for why our universe possesses certain properties and why the laws of physics appear finely tuned for structure formation. Some researchers have even proposed forms of cosmic natural selection, where universes producing large numbers of black holes generate more offspring universes and therefore become more common over cosmic time. Quantum mechanics adds another layer of mystery. Some theoretical frameworks suggest that black holes may preserve information in subtle ways not yet fully understood. Instead of destroying information, they may encode it within quantum structures associated with the event horizon. If true, black holes could be connected to deep principles governing the nature of reality itself. Concepts such as quantum entanglement, holography, and emergent spacetime increasingly appear in attempts to understand these objects. One particularly intriguing proposal emerged from studies of quantum entanglement. Some physicists have suggested a relationship between wormholes and entangled particles, summarized by the phrase ER equals EPR. While highly technical, the idea hints that connections between distant regions of space may be fundamentally related to quantum relationships between particles. If correct, black holes could play a central role in unifying gravity and quantum mechanics. For our spacecraft crew, however, these possibilities remain purely theoretical. They continue falling deeper into the black hole with no guarantee that any wormhole, white hole, or alternate universe exists ahead. The equations offer possibilities, not certainties. Every kilometer traveled brings them closer to regions where known physics becomes increasingly uncertain. The beauty of black hole research lies precisely in this uncertainty. These objects force scientists to confront the limits of current knowledge. They sit at the intersection of gravity, quantum mechanics, cosmology, and information theory. Every attempt to understand them reveals deeper questions about reality itself. Whether black holes are simple gravitational traps or gateways to entirely new realms remains unknown. For now, the evidence supports a cautious conclusion. No observation confirms that black holes connect to other universes. No traveler has returned from beyond the event horizon. Yet the mathematics continues to hint at possibilities so extraordinary that physicists cannot ignore them. Somewhere within the deepest equations describing space and time may lie answers capable of transforming our understanding of existence. As our journey continues, we leave behind the speculative realm of wormholes and alternate universes and return to a question grounded firmly in physics. Black holes are not eternal. Even these cosmic giants have lifespans. They grow, evolve, and eventually face their own fate. To understand the complete story of black holes, we must now look far into the future and explore what happens when the universe itself begins to change around them. Black holes often seem eternal. They are so massive, so powerful, and so difficult to destroy that it is easy to imagine them existing forever. Entire stars fall into them. Galaxies grow around them. Billions of years pass while they remain hidden in the darkness of space. Yet one of the most surprising discoveries in modern physics revealed that black holes are not immortal. Like stars, galaxies, and perhaps even the universe itself, black holes have lifetimes. They are born, they evolve, and eventually they die. Understanding their fate requires us to journey not only to the edge of a black hole but also to the farthest future imaginable, a time when the universe will look completely different from the one we know today. For much of the 20th century, physicists believed black holes could only grow. Matter falls inward. Gas accumulates. Stars are consumed. Nothing escapes. According to this picture, black holes would gradually become larger over time. Then, in the 1970s, Stephen Hawking made a discovery that transformed black hole physics forever. By combining ideas from quantum mechanics and general relativity, Hawking showed that black holes are not entirely black. Instead, they emit tiny amounts of radiation. This phenomenon is now known as Hawking radiation. The process arises from quantum fluctuations occurring near the event horizon. According to quantum theory, empty space is not truly empty. Tiny particle-antiparticle pairs constantly appear and disappear throughout the vacuum. Normally these pairs annihilate each other almost immediately. Near a black hole, however, gravity can separate them before annihilation occurs. One particle falls into the black hole while the other escapes into space. To distant observers, it appears as though the black hole itself is emitting particles. The result is a slow loss of mass and energy. For stellar mass black holes, Hawking radiation is incredibly weak. The radiation emitted is far smaller than the energy absorbed from the surrounding universe. As a result, such black holes continue growing rather than shrinking. Yet if enough time passes, the situation changes. Stars eventually die. Galaxies evolve. Sources of matter become increasingly rare. In the extremely distant future, black holes may find themselves isolated in a cold and dark universe. At that point, Hawking radiation begins dominating their evolution. The timescales involved are almost impossible to comprehend. The Sun will exhaust its nuclear fuel in approximately 5 billion years. Most stars in the Milky Way will disappear within trillions of years. Yet a typical stellar black hole may survive for around 10 years before completely evaporating through Hawking radiation. To appreciate the magnitude of this number, consider that the universe itself is currently only about 13.8 billion years old. The future lifetime of a black hole exceeds the current age of the universe by an unimaginable factor. Supermassive black holes live even longer. The giant black hole at the center of the Milky Way contains roughly 4 million solar masses. Its evaporation time is estimated to be around 10 years. The largest known black holes may survive for over 10 to the power of 1 years. These numbers are so enormous that ordinary language struggles to describe them. Entire eras of cosmic history unfold before black holes begin approaching their final moments. During this distant future, the universe itself undergoes dramatic changes. Galaxies gradually drift apart due to cosmic expansion. Star formation slows and eventually ceases. Existing stars burn out. White dwarfs cool into black dwarfs. Neutron stars fade. The universe becomes increasingly dark. Physicists often refer to this period as the degenerate era, followed by the black hole era. During these epochs, black holes become the dominant objects in the cosmos. Imagine looking out across the universe during the black hole era. No bright stars illuminate the darkness. No galaxies shine across the void. Instead, enormous black holes drift through an expanding cosmos. They occasionally merge, producing larger black holes. Yet even these giants are slowly losing mass through Hawking radiation. The process is extraordinarily slow, but it never stops. As a black hole shrinks, its temperature increases. This is another surprising consequence of Hawking's discovery. Most objects cool as they lose energy. Black holes behave differently. Smaller black holes become hotter and emit radiation more rapidly. The evaporation process accelerates over time. For billions upon billions of years, almost nothing seems to happen. Then, near the end, the black hole begins disappearing more quickly. The final moments remain uncertain because current physics cannot fully describe conditions at such small scales. Nevertheless, most theories predict a dramatic conclusion. After losing nearly all its mass, the black hole may release a burst of energy before vanishing completely. The object that once dominated entire regions of space simply ceases to exist. The event horizon disappears. The black hole becomes part of history. This outcome raises one of the deepest questions in theoretical physics. What happens to the information that entered the black hole? If the black hole evaporates entirely, does the information vanish as well? Quantum mechanics insists that information must be preserved. Hawking's original calculations seem to suggest otherwise. Resolving this contradiction became one of the greatest challenges in modern science and remains closely tied to the black hole information paradox. The fate of black holes is therefore connected to the fate of the universe itself. Understanding one may require understanding the other. Some cosmological models predict that the universe will continue expanding forever. In such scenarios, black hole evaporation becomes a major chapter in cosmic history. Other theories suggest more exotic futures involving cyclic universes, quantum transitions, or entirely new phases of reality. Black holes appear in nearly all these discussions because they represent the most extreme environments known to physics. For the crew of our imaginary spacecraft, these distant futures may seem irrelevant. They continue falling deeper into the black hole, moving toward the singularity hidden at the center. Yet from a cosmic perspective, the story of black holes extends far beyond any individual journey. These objects are not merely destinations. They are active participants in the evolution of galaxies, the distribution of matter, and perhaps the ultimate destiny of the cosmos itself. The realization that black holes can eventually disappear is both surprising and profound. Objects once considered eternal are revealed to be temporary. Even the most powerful gravitational structures in the universe are subject to change. Time eventually transforms everything. Yet despite everything we have learned, one mystery remains larger than all the others. Black holes challenge our understanding of gravity, quantum mechanics, information, and the nature of reality itself. They force us to confront questions that may require entirely new physics to answer. As our journey approaches its conclusion, we must step back and ask what black holes have truly taught us, not only about the universe, but about humanity's quest to understand the deepest secrets of existence. Our journey began with the death of a star. From that moment, we followed gravity to its most extreme conclusion and traveled toward one of the greatest mysteries in the universe. Along the way, we encountered warped space, distorted time, invisible boundaries, supermassive giants, quantum paradoxes, and possibilities that stretch the limits of imagination. Few objects in nature challenge human understanding as profoundly as black holes. They are not simply astronomical curiosities. They are cosmic laboratories where the laws of physics are tested under conditions impossible to recreate anywhere else. And perhaps more importantly, they reveal how much humanity still has to learn about the universe. For centuries, black holes existed only as mathematical possibilities. Even Einstein, whose equations predicted them, was uncomfortable with the idea that gravity could become so powerful that not even light could escape. Yet nature proved stranger than anyone expected. Observations gradually revealed invisible objects influencing stars, emitting powerful radiation through accretion disks, and shaping the evolution of entire galaxies. Eventually, humanity obtained direct images of black hole shadows, transforming theoretical predictions into observed reality. What once seemed impossible became one of the greatest scientific discoveries in history. Throughout our exploration, one theme appeared again and again: gravity is far more than a force. Near black holes, gravity reshapes space and time themselves. Distances become distorted. Light bends into impossible paths. Clocks tick at different rates. The familiar universe gives way to a reality governed by principles that often defy common sense. Yet despite their strangeness, black holes obey precise mathematical laws. The same equations that describe falling apples and planetary orbits also describe the behavior of these cosmic monsters. This connection is one of the great triumphs of physics. Perhaps the most astonishing lesson concerns time. Near a black hole, time itself becomes flexible. Observers experience reality differently depending on where they are located. A journey lasting hours for one traveler may correspond to years, centuries, or longer elsewhere. The idea that time can flow at different rates once seemed absurd. Today it is a confirmed aspect of nature. Black holes demonstrate this fact more dramatically than any other object in the universe. We also encountered the event horizon, the ultimate point of no return. This invisible boundary is not a wall or a physical surface. It is a limit built into the structure of space-time itself. Crossing it changes the future forever. Beyond the horizon, escape becomes impossible. Every path leads inward. Few concepts in science are as simple and yet as profound. The event horizon marks the edge of the observable and the beginning of the unknowable. Deeper inside, we confronted the singularity. According to classical general relativity, this is a region where density becomes infinite and the known laws of physics cease functioning. Whether singularities truly exist remains one of the greatest open questions in science. Most physicists suspect that a future theory of quantum gravity will replace the singularity with something else entirely. Yet until such a theory is discovered, the center of a black hole remains one of the most mysterious locations imaginable. The journey also revealed that black holes are not isolated objects drifting passively through space. Supermassive black holes influence entire galaxies. They regulate star formation, power quasars, and shape cosmic evolution on enormous scales. The giant black hole at the center of the Milky Way is only one example among billions scattered throughout the universe. Wherever astronomers look, black holes appear connected to the growth and history of galaxies themselves. Then came the paradoxes. Hawking radiation showed that black holes are not truly black. They slowly evaporate over unimaginable timescales. Yet this discovery created the information paradox, forcing physicists to confront deep contradictions between quantum mechanics and general relativity. Information, entropy, space-time, and quantum theory all collide at the edge of a black hole. Solving these puzzles may eventually lead to a unified understanding of nature itself. and perhaps most fascinating of all are the questions that remain unanswered. Could black holes contain wormholes? Do they connect to other universes? Is our own universe somehow related to a black hole existing elsewhere? These ideas remain speculative, but they demonstrate how black holes continue inspiring new ways of thinking about reality. Every answer seems to generate even deeper questions. In many ways, black holes symbolize the frontier of human knowledge. They remind us that despite all our achievements, we still stand at the beginning of understanding the cosmos. Humanity has mapped planets, explored the solar system, observed distant galaxies, and measured the age of the universe. Yet black holes continue guarding secrets that challenge the most brilliant minds on Earth. Somewhere within their mysteries may lie clues to a deeper theory of reality, one capable of uniting gravity and quantum mechanics into a single framework. As we conclude this journey, it is worth remembering how extraordinary it is that human beings can even ask these questions. We are a species living on a small planet orbiting an ordinary star in the outskirts of the Milky Way. Yet through curiosity, mathematics, and observation, we have learned about objects billions of light years away. We have predicted phenomena before seeing them. We have uncovered invisible structures hidden within the darkness of space. The story of black holes is therefore not only a story about the universe. It is also a story about humanity's desire to understand its place within it. Somewhere in the darkness beyond the stars, countless black holes continue their silent existence. They consume matter, bend light, warp time, and shape galaxies. They hide behind event horizons that no information can cross. They challenge every assumption we make about reality. And perhaps, deep within their mysteries, they hold answers to questions we have not yet learned to ask. Thank you for joining this journey to the edge of a black hole. If you enjoyed exploring the deepest mysteries of space and want to support more long-form documentaries like this one, don't forget to subscribe to the channel. Your support helps bring more incredible journeys through the universe to life. Until next time, keep looking up, because the cosmos still holds countless secrets waiting to be discovered. Even after more than a century of scientific investigation, black holes remain among the most mysterious objects ever discovered. We have learned how they form from dying stars. We have studied their immense gravity. We have observed the influence they exert on galaxies. We have photographed their shadows and detected the collisions of black holes through gravitational waves rippling across the universe. Yet despite these achievements, humanity still does not fully understand what happens beyond the event horizon. In many ways, the story of black holes is only beginning. The next generation of telescopes promises to reveal more than ever before. Future observatories will capture sharper images of black holes, allowing astronomers to study their environments in unprecedented detail. Scientists hope to observe the behavior of matter orbiting close to event horizons and test Einstein's theory of general relativity under the most extreme conditions possible. Every new observation offers an opportunity to uncover clues about the true nature of space and time. Gravitational wave astronomy is also opening an entirely new window into the universe. Before 2015, black hole mergers were purely theoretical events. Today, detectors regularly observe the ripples produced when black holes collide. These signals allow scientists to study objects that emit no light and would otherwise remain invisible. As technology improves, future detectors may uncover thousands of new mergers, revealing how black holes grow, evolve, and interact across cosmic history. At the same time, physicists continue searching for a theory that unites gravity and quantum mechanics. Black holes sit at the center of this quest because they force both theories to operate together. The information paradox, Hawking radiation, and the mystery of the singularity all point toward gaps in our understanding. Many researchers believe that solving these problems could lead to one of the greatest scientific breakthroughs in history, a complete theory of quantum gravity capable of explaining the deepest workings of reality. Perhaps the most exciting possibility is that black holes may teach us something entirely unexpected. Throughout history, major discoveries often arrived when scientists explored phenomena they did not fully understand. Black holes may ultimately reveal new dimensions, new laws of physics, or entirely new ways of thinking about the universe. They may help explain the origin of space and time. They may uncover connections between information and reality itself. Or they may show that the cosmos is even stranger than we currently imagine. As we conclude this journey, one fact stands above all others. Black holes are not merely regions of darkness hidden in distant corners of space. They are fundamental components of the universe. They shape galaxies, influence cosmic evolution, and challenge the limits of human knowledge. Every question they raise pushes science forward. Every mystery they present inspires new generations of researchers to look deeper into the cosmos. Somewhere out there, beyond countless stars and galaxies, billions of black holes continue their silent existence. They bend light, warp time, and guard secrets hidden behind their event horizons. We may not yet know what lies at their centers, but humanity's curiosity has never been stronger. With every new telescope, every new theory, and every new discovery, we move a little closer to understanding these extraordinary objects. Thank you for joining this complete journey to the edge of a black hole. If you enjoyed this documentary, please consider subscribing to the channel. Your support helps bring more deep space explorations, cosmic mysteries, and long-form astronomy documentaries to life. Until our next adventure, keep looking toward the stars, because the universe still holds countless wonders waiting to be discovered.